we're working our way up the protocol stack. We're in the network layer. We did an overview, and we're working our way up from the physical layer to the data link layer, network, transport, and application layer with a focus on the security issues going up and down the protocol stack. And so probably in some of the other courses you might be taking, you're looking at protocols for different purposes. We're looking at just breaking them. And I think actually learning how to break a protocol really gets you to understand how the whole protocol works. So we are with ARP right now. And one of the things before I start with ARP, I want to introduce this tool, Nmap, which is I'm going to have you use throughout the network layer. And this is a de facto, it's an open source tool, and it's used by everyone to do things like explore networks to see what machines are on there, to scan different services to see if they're vulnerable to things. Nmap and Metasploit are two of these tools. If you do any security certification, you're going to need to know how to use Nmap. This is just a gentle introduction to its use. Nmap, if you look at the Nmap man pages, it's enormous because there are so many different things you can do. Query a network, a lot of different protocols to poke. And I'm just going to give you a tiny sample just to show you kind of the diversity of functions that it can provide you. And that's the idea. So it's a scriptable tool to basically programmatically probe and scan the network. There are many flags, as I said before, some example scans that we'll be doing with this tool. And this is why I introduced it here, because the very first scan I'm going to show you is the ARP scan. But as we go up the network stack, there are some network layer scans, there's some transport layer scan, and then at the very top, there's going to be some content-based scans where we're actually hitting it with a particular protocol, application protocol. And this is just one tool that is very effective at what it does. Okay, I just wanted to introduce that tool. We're going to start with the ARP, Address Resolution Protocol. This protocol is a data link layer protocol, and this governs how we transmit data from hop to hop, from this laptop to that base station, for example. And so here's a picture of a local area network. They all share the same physical medium. And you have a network here on the bottom left, host A, with this IP address 10.0.0.11. And it wants to directly communicate with host B, but all it has is host B's IP address, which is 10.0.0.22. And how does it figure out the hardware address that host B is using? So we said earlier that hardware addresses are the way we can train at the physical layer to and from point to point. So you have these two hosts with two IP addresses, and they have distinct hardware addresses. The ARP resolution protocol allows A to ask for the hardware address of B if A knows B's IP address. And the way it does this is that it sends a broadcast frame using a destination hardware address of all one. And then it uses its own MAC address as the source for this frame. And it basically crafts this ARP request that's broadcast throughout the network. And then B is listening. Well, all of these devices on this network are listening for frames. And as soon as they see the broadcast, they will all process the broadcast. And if it's the IP address that they own, they are supposed to respond with a reply. Okay. When B receives this ARP packet, it will respond back to A with a frame that's directly intended to go back to A, because A has supplied their source MAC address as part of the query, and the destination MAC address. So the destination MAC address is A, and then it'll use its own MAC address as the source. So this is an animation. Well, this is partway through. The thing finish. So A broadcasts this ARP request. It says, "Hey, I need 10.0.0.22." And then host B is like, hey, that's for me. I'm going to send this reply. My MAC address is what it says, BBB. And that's how the ARP protocol. On the other side, A is going to take that reply and say, you know what, I don't want to have to do another ARP. I don't want to ARP every single time I'm looking for B. I already know what B is now. I'm going to sit there and hash that. And this is a local ARP table that the machine host A keeps that says, I'm going to keep track of this resolution. And this is a soft state protocol. It says for 60 seconds, I won't ask for 10.0022. I'll just directly send it to the MAC address I found earlier. Now, this ARP cache on Linux, you can get at this cache using ARP-A in the command line, or you can go into the /proc file system and procnet ARP is a machine-wide ARP table that also has it. Okay. So ARP scans nmap-PR. This is a way of enumerating all the addresses, all the hardware addresses that are on your LAN. And so this is the idea is that I'm going to ARP for every single IP address that's directly connected to me and figure out which one will reply to me. Okay, so that's just basic inventory. If the host is up, it'll send me the reply. If the host is down, I'll get a timeout because nobody's going to respond to this request. Okay, so that's a very common thing. And this is all done as part of network discovery to identify targets on a local area network. An adversary gets onto a machine. One of the things the adversary could do is just an ARP scan and figure out what's also directly connected to me. And this is the default setting for Nmap. When you're scanning an address on the same network as the scanner, it will automatically be done. You actually have to explicitly tell Nmap not to do this if you want to be more targeted. And we'll talk about stealth scans, because if you're doing this, someone's going to notice. It's like, why is this particular address asking for every single MAC address of every single IP address on the network? And so adversaries are like, okay, if the defender is smart and is looking for this scan, I don't want this by default to be done. And we'll talk about sneaky scan later on in this class. Okay, note that because ARP is basically a link layer scan, you can't ARP for an IP address that's not part of your directly connected network. So here's an example of someone doing an ARP about the subnet. So you can see for searching 0.0, 0.1, 0.2, all the way to 0.255. And in this case, you see someone replies. This machine replies. And so you see there is a host on 192.168.0.1. And then this would also reply to itself. So scan is being done by 0.33. Because it won't route. When you do an ARP, request, a broadcast for a particular IP address, only those machines that are connected to that network will have an IP address that matches the. And if it's a remote, right? Yeah, then it won't get forwarded. The ARP broadcast will not get forwarded, and so you're confined to the network that you're connected to. Yeah. That's a picture of it. Okay, so then the question is what happens if two machines are vying for a single IP address? Say you're statically configuring your addresses and you just so happen to use the exact same address. Or maybe you're using DHCP and someone joins your network that has a statically configured IP address that just so happens to match you. Then you got a problem, right? You're like, okay, well, which one is the legitimate one? And that's the question you would ask on this particular trace. You're sitting here, you're looking at this trace, and one of the things with ARP is that the last reply will always be considered to be the legitimate one. It's the fresh one. It's the most recent information. And so in this trace, at the end of this trace, which ARP reply will be used by the red one or the green one? Which one's the last one? The red one. Which one do you think is likely the correct ARP reply? Which one do you think is legitimate or not? It's hard to judge intent on a packet trace, but which one would you rather have your machine use? The green one. The red one is sitting there, I'm owning this IP address regardless of whether or not someone asked me to. Yeah, unsolicited even, eh? Like you don't see an ARP request, and then this machine is telling you, hey, this IP address is me, 22.13, and here it is again. And if someone slips in there and tries to undo that reply, I'm going to send another one and make sure that is undone. So how do you disambiguate this? How would you? And you think that this is a problem? Turns out it is a problem. It's called ARP spoofing. So ARP is not an authenticated protocol. So there is no source integrity being done, or well, integrity, I guess you could say, is kind of being done by the data link layer, but there's no source integrity being done in the protocol. And it can be used compromise confidentiality because you can actually inject yourself into the middle of a communication by spoofing ARP of a legitimate destination and then putting all that destination's traffic and then forwarding it on to the network. So this is an example of source integrity and potentially data integrity and confidentiality with a person in the middle attack. And this is something we're going to see throughout protocols. Because, as it turns out, the internet protocols, when they were designed, didn't have this in mind, right? This kind of behavior. Okay, so here's what it looks like. The idea is that the adversary, sitting right over here, is on this network, and this is a switch. So this effectively puts all of these machines on the same local area network. So a switch is just a data link layer device. When the ARP is broadcast, it gets copied onto all the ports of the switch, and the router and the adversary are connected to this switch. And so if this PC here is ARPing for the router should be the only one to respond. Instead, the adversary is like, you know what, I want to be the router. And so I send this red packet. And then this is how I spoof the response from the router and then get PC1 to communicate to me 1.6 as the router instead of the legitimate router. So when this happens, all the adversary needs to do is then configure his or her machine to then take any packets from PC1, slurp them up, and then forward them back out to the real router. And this is what you end up getting, this person in the middle attack on your local area network. So again, source integrity, ARP doesn't have source integrity, and this leads to both a data integrity and a confidentiality attack in the middle here, where this adversary is now able to inject traffic and to reveal traffic going through. Okay, about this one, because it's being used. Typically, this is a common attack on SCADA networks. So when you talk about critical infrastructure, where you have some kind of controller machine and you have some critical microcontroller, like a centrifuge in a nuclear power plant or something like that. And so you have this human machine interface over here, connected over a switch perhaps, some programmable logic controller, and the idea is that you get real-time updates from this controller and you can actuate things, control that thing. And if it's all connected into a switch, then all you would want to do is say you have a machine on this network that you have hijacked, then what you can do with this compromised host is if you know that these things are communicating, you can inject unsolicited ARP replies in stream, and you can trick the HMI to believing that the hardware address of the PLC is the compromised host, and the PLC you can trick into believing that the hardware address of the HMI is also the compromised host. Okay, And this is what you end up with, where the communication goes through this compromised host and to and from the PLC and the HMI. Okay, so this is, I forget which article I pulled this out of, but this has been found in the wild in industrial control systems. Then the question is, can we detect it? So poisoning attacks, I'm going to give you a hint as to how you might detect something like this. Poisoning attacks require some interface on that network to be capturing every single packet and to be potentially responding to every single packet. And as part of this, the attacker has to turn on what's known as promiscuous mode in their network adapter. And so most of these adapters are programmed to drop traffic that isn't destined for its hardware address, because it's like, I don't want to wake up the operating system to handle this because it's not meant for me, right? But most of the time, data link layer frames are ignored if they don't match the hardware address of the adapter. You have to tell your adapter to like, give me everything, and that's called promiscuous. And typically to turn that on a machine, like a Linux machine, you have to have super user privileges or whatever that capability is to be able to slurp up all of the traffic on a machine. So one way to detect this is that if you're on that local machine, you can just do an if config-a and look for whether or not the promiscuous mode has been enabled. And this is assuming the attacker hasn't hijacked your operating system. Why? One way. What about someone running an interface in promiscuous mode somewhere in your network? Like, how do I know? Got like what, 8 laptops here in this room. How do I know if one of you? I'm assuming we're all on the same network. How do I know if one of you is slurping up all the frames? I'd be able to test the network. What do you think? I like students to kind of brainstorm on how would I reveal this behavior. Okay, so yeah, one way is for you to turn on promiscuous mode and monitor the ARP replies. So that's one way. You say, hey, this person isn't legitimately replying to actual requests. Then the attacker's sneaky. The attacker is just going to wait for an ARP request and then race the legitimate router in this case to reply. Then it would be harder to So, anyone else want to guess how we're going to figure this out? One way to figure this out. The way to figure this out is to send a packet, just a bogus destination MAC address to an IP address, and to all the different IP addresses that might be directly connected to you. And it's only the one listening for everything that will respond to it, right? Because the promiscuous mode will take that data link layer frame, will slurp it up, pull out the frame, and then send it into the operating system. And it's only that machine that will respond with TCP SYN packet, assuming that it has a server that it's running, right? So that's why you want to be, like, if you're an adversary on a network, you kind of want to be stealthy. Underneath, then and the cat and mouse game that Nmap is helping me play, both for good and for. Why is because it's a bogus MAC address. You should get no response, right? Zero probability on that packet. Because most network interface cards are like, oh, that. But if the adversary is listening to, if you get a legitimate IP address IP packet for that. Then you give it a focused MAC address. It's only the promiscuous adapter that will say, oh, I'm going to take that packet and then give you the IP packet. Most NIC, most network interface cards will drop it. That's not, even though the IP address matches both, right? That's how you would detect that particular one. Yeah. Oh, you would have to intentionally do this. Yeah. So that's why you have to know to look for this, right? And you could, I think you can use Nmap to do this kind of thing. See if someone is doing. Yeah. Okay. Yeah. It typically will respond. So the website, you have to actually know that there's something that's going to respond, and it will respond back to you. You didn't. You're legitimately trying to connect to a TCP connection. All you're doing is faking the data link layer frame. Make sure that nobody on the network blurted it up. But if someone does and responds to that, they're a promiscuous interface. Yeah. I don't have a lab that does this. It's kind of a whole bunch of work for very little benefit, but this is something you could. Yeah, no, it would take a lot of work. There is oh no, I won't describe that. Any questions about this? Yeah, this is called ARP poisoning, where you're poisoning the cache that your victim is going to use to communicate to other devices. Yeah. Not sure. Yeah, don't know what that what that refers to. Okay. All right, so that's the data link. That's all I'm going to cover in the data link layer. I'm going to move on to the network layer, which has much more interesting stuff, attacks to cover. Okay, so the next layer in the stack is the network layer. I'm going to do just a brief overview of the network layer and with regards to the things that we're going to cover for network security. This is a picture of the internet network layer. You have some routing protocols that determine where packets go in the network. You have the actual IP protocol that is used to frame the data or send packets. And then you have a control message protocol for error reporting and router signaling. I'm going to first start with the IP, an overview of the function IP provides, and this is super easy because it doesn't provide much of anything. I'm going to talk about the delivery semantics. So the internet protocol is basically a datagram service. There are no support for network layer connections. Those things have to be provided at the end host using a transport layer connection. There are no reliability guarantees for IP packets. There are no ordering guarantees. There is no broadcast or multicast that IP supports. It's mostly unicast point-to-point communication, but there is some support for what they call anycast. And this is an IP address that has a whole bunch of machines that can respond to that particular IP address. And the semantic is reach any one of them, and whichever one you reach first is fine to use as that address. And this is done with some routing protocol hack. The example of anycast that I show people usually is Cloudflare. This is a DNS resolver that you can use anywhere, and it basically points you to Cloudflare's nearest DNS resolver. And the nearest one in Portland is in the Pittock block, which is downtown Portland. But if you go to a different city, 1.1.1.1 will be somewhere very local to that particular region. Okay. This is a picture of the datagram a version number. The things that I want to talk about are this set of headers, the fragmentation support, the upper layer, which is where do you deliver this IP packet to when it hits the destination, and then the source IP and the destination IP addresses are what we're going to look at. But then, so you have a data link layer frame, which is the outer DAL. This is the next innermost DAL, and then within this DAL, you have a TCP segment as the lower embedded DAL. So that's just to recap that Russian doll analogy for packets on the internet. Okay, so I said I was going to look at the protocol fields of interest when it comes to network security. The first one is this protocol type field, and this basically points to what is the data type or the protocol type of payload that I'm carrying, and that's what here. And this is typically a TCP segment, a UDP segment. It also could be an ICMP packet. So that's what this protocol type will indicate. So I said earlier, it could be a transport layer. And these are the numbers in that protocol field. So you can see that this protocol field is basically what is an 8, like the upper layer is an 8 number. And so that's what you see here. And then the other important protocol type are the tunneling ones. And so Russian dolls can be structured arbitrarily. You can have a network packet inside of a data link layer frame, which is also carried in a network layer packet and a data link layer frame. And so the way this tunneling works is through these headers. So there's when you want to carry IPv6 packets within IPv4 network, you can use tunneling to wrap another Russian doll layer around a network layer packet. Type 41, and then generic routing encapsulation allows you to do this, create virtual networks on cloud platforms. And so this encapsulation is something that we'll be using when we're talking about virtual private networks and virtual private clouds later on in this layer. The other thing I want to talk about are the fragmentation field. So anytime you have a network layer packet that is much bigger than the data link layer maximum. So every data link layer has a maximum frame. Process fragments forwarded eventually back to the end, all the way to the end host. And it's only at the end host that you reassemble the original IP packet and then send it up. Now I'm covering this because this is an avenue for denial of service. But as it turns out, you can actually cause a denial of service attack on the recipient if you give it a whole bunch of fragments that don't have things that will complete it, partial fragments. And the operating system on the other side has to buffer all of those fragments, waiting for that fragment to complete each one of these things so that it can send it up the protocol stack. This is just one way to sap all of the buffer space on the recipient. The other thing that you can do with fragmentation is that you can use it to evade detection of your attack. And so one of the things that people do in the network is to try and slurp up all the traffic, analyze the payload, figure out what's being sent. And one of the things you can do is you can split your attack across multiple fragments, confuse the monitor in the network. And moreover, you can sometimes overlap the fragments so that their byte ranges overlap. And then you'll confuse the monitor as to, well, what is the legitimate data that the victim might actually use when they do their reconstruction. And so, like, when you have an overlapping fragment, then you have an algorithm problem where you use the the overlap one first, or do you use the original one first, the bytes from the original one? And that difference in semantic can allow you to slide under the radar, slide your attack under the radar. Okay, so they removed it in IPv6. They're like, no, we're not going to do this. What they do in IPv6 is that they force the client to do a path MPU discovery thing that the end host has to figure out the smallest, the size of the packet that it needs to have in order to make it all the way through the network. If it's too big and it happens to hit a data link layer where that packet is too big for that data link layer, in IPv6, you just drop it. You drop the packet. You don't try and forward it. Okay, I'm going to talk about the different things that IP provides. I'm going to first talk about IP routing. So the internet protocol does its routing via hop-by-hop forwarding based on only one thing: destination IP address. And as a result, every router in the network has a routing table or a forwarding table that says for a particular destination IP address, I'm going to look up into this table, figure out what is the next hop interface and the next hop of the IP address that I need to forward this packet. In order to generate this forwarding table, every router on the internet has to run a routing this table that arbitrary packets can be forwarded to their destination. Now you can think of this problem and be like, wow, that's a lot, that's an enormous routing protocol and an enormous forwarding table that every router has to keep track of. And that's a problem. So if you do this in a flat manner, where every single router has to communicate with every other router to figure out a routing table, this doesn't scale. You got more than 200 million destination network. You can't store this efficiently. You can't compute this efficiently. And it's going to take you a whole bunch of bandwidth to exchange topology information. That's one problem. The other problem with a flat network is that you really want autonomy of managing network, and you want them to be isolated from each other. The operational sort of intricacies of one provider shouldn't impact someone else's, another provider's network. So this isolation is something that you also want, so that administrators can basically autonomously control their own infrastructure. So for example, when Portland State starts changing things internally, their network architecture internally, you don't want people at Oregon State, right, or somewhere across the country to see that. And so both of these two things, both of these routing issues lead to the internet routing hierarchy. And the key observation here is that you need a lot less routing information the further you are away from your destination. And this allows you to save table size and reduce the amount of update traffic that's going on. And this is implemented through a notion called autonomous systems, or ASs. This comes up all the time when you're doing network security, because you want to know which AS has sourced any attack traffic that you have received. Then you need to talk to that AS and say, you're launching abusive, someone on your network is trying to abuse my network destinations, you better do something about it. And this is what happens at Portland State all the time. This is why OIT doesn't like me running certain kinds of things, because they'll get complaints from other people that they must address if it comes from them. So, because their autonomous system that Portland State runs has a number, and if people see traffic from those IP addresses that are attack traffic, then it's Portland State's on the hook for that. Okay. So the idea of the hierarchy is that we have these ASs, and then within the AS, you run a full-on routing protocol. So you do, and this is called an intra-AS protocol, where every node in the AS knows every other node in that AS, and then the routing operation within it. Then there are special nodes in that AS. There are border routers that are at the edge where they communicate outside of the AS to other ASs. So eventually your traffic will need, like if it's going to like Google, eventually you're gonna have to get out of the state AS and then go to other ASs to reach Google, basically. Okay, so ASs, so between Portland State and other destination, you will run an inter-AS protocol, and that's typically with this Border Gateway Routing Protocol, or BGP. And this is basically handling the routing that's done between ASs on top of the, I guess, the individual AS. And this treats each AS as a node in a graph. So this is how it looks. This is what it looks like. Say I have these three ASs, A, B, and C, capital A, B, and C. What happens is, let's start with ISP-B. ISP-B has these internal nodes, little a, b, and c, and then it has a border router, B.A, and this border router communicates to other autonomous systems. And within ISP-B, all of these routers have information going to each other. Basically, between ASs, the only thing that A and C know about B is this one border router. And in that way, these internal routers are hidden from the other parts of the network. Addresses in C are likewise combined, and then the only node that other ISP-C and in ISP-C is C.B. And then those internal nodes are hidden. And then likewise for A has two border routers, little a and little c. And so you have this where the internal nodes within capital A are then hidden. Now you have these border routers, and between these border routers is what you'll run BGP with. So BGP is being done between these border routers, and this is effectively creating an overlay network, right? You know, you're hiding complexity of these ASs, and you're creating this sort of a logical overlay network on top of a physical one, okay? And this happens all the time in networking. And we'll see a logical overlay when we talk about the internet protocol itself, because the internet protocol is a logical overlay on top of a bunch of link layer question. So your home network has a whole bunch of machines on it. External from your home, you present a single node to your ISP. So your ISP doesn't know your backend architecture because you've hidden it on this one IP address, and you're using a whole bunch of private IP addresses. Yeah, it's an analogous. Yeah. So this is what it looks like. You typically have these large global providers, tier 1 ISPs, have points of presence throughout the globe, and then they'll peer with regional ones or local ISPs in order to sort of create a sort of a logical overlay across on top of all of these individual routers. And this hierarchy is how you can scale up internet routing. Okay. So you'll have a packet that will end up passing through a whole bunch of different ISPs on its way to its final destination. Okay, so the problem here is that there could be an adversary anywhere in this traversal. And so we have different ASs, we have adversaries inside of different ASs. And so if there's some funny business that's going on, these are the tools that we need to kind of zero in. This is especially important for attribution. Like if you're trying to figure out who did what where in the network, you need this level of detail. Okay, so let's talk about BGP and inter-AS thing. The thing I want to talk about is that BGP messages are exchanged using TCP. And as it turns out, when we designed BGP, we didn't build in authentication. So yeah, this is not like TLS. The route advertisements that these border routers are sending to each other are not authenticated. There's no public key infrastructure for setting up a router. There was, I mean, it was impossible to out before we started routing itself. It's only later on. Before we can talk about attacks on routing, we have to talk a little bit about IP. Header, there's a 32-bit identifier for both the source IP address and the destination IP address. 0 to 255 or hex 00 to hex FF. And so here's an example of the states 131.252.220.1. Each one of these integers specifies a decimal representation of one of the 4 bytes. And so here is 131 in binary. So that first byte, and then 52, 20, and 1. And so this is basically, these bits are what are included in that IP header in that packet. So given that there are 32 bits, what are the total number of addresses available for use? Well, actually not, this is old actually. S2.1, we teach that as a 32-bit architecture. It's been 5 years since I've taught 201. Now it's 64-bit, but like 32 bits is basically 4 billion addresses. That's like, okay, so IP addresses. So you might think that an IP address is associated with a machine or device, but it's not. It's associated with a network interface on the device. And devices can have multiple network interfaces, so they can have multiple IP addresses on them. Routers, by definition, they're taking a packet from one IP network and sending it to another IP network. By definition, they must have multiple IP addresses. Whereas a host can have one IP address, but if you have multiple network interfaces, like maybe I have a cell that has a cellular network that's enabled, the Wi-Fi is also enabled, it might have 2 IP addresses too. That's 2 network interfaces. So that's the idea of associating addresses with interfaces and not machines. One of the things that we talked about was aggregating route and addressing, IP addressing and route aggregation. Domain routing. So the idea is if you have this ISP, like ISP is what we started out with slides ago, and you're trying to advertise a route, all the nodes in your ISP using a single route advertisement, you're going to need to describe those addresses that you want for that route using CIDR. And this is what I'm going to teach. And what it is a way of denoting a sequential block of IP addresses whose size is the power of 2. Okay, let's talk about this. The idea is to take these adjacent addresses, adjacent IP addresses, and glom them all together in what we call an operation called supernetting, to describe a larger aggregate out of a whole bunch of smaller pieces of address space. On the other side, if you're given a large block of addresses, the reverse of that is to do a subnetting operation where you're splitting this large block into individual smaller blocks underneath. I'm going to talk about both of these, and these are ways of describing ranges of IP address, and that's what internet routing is done on. Okay, the notation of CIDR is a network, basically a 32-bit IP address, and the number of bits in the prefix that note the block, the size of the block. So here's an example. I have this network prefix 223.16.0. And you have a number of bits in the prefix that the addresses in this range match to. So the first 23 bits of this network prefix are what is shared across all the IP addresses you're describing with this notation. So the way this works is you take the 200.23.16.0 and you expand out the binary for it. And then, so this is 32 bits. And then you count off the first 23 bits. And so this is the first 23, this is the 24th, and then this is that last byte. And so the variable part of this network prefix is at the front, and we call this the network part. And then all of the hosts, all of the IP addresses that this prefix corresponds to will have patterns match this variable part, and then the host part can be anything. It could be a wildcard. So in this case, the host part can be either all zeros all the way up to all ones. And so this denotes a range that is a power of 2. And in particular, it's a power of 2 with 9 bits, right? So this is the 9th that correspond to this prefix. And this is basically describing IP addresses from 200.23.16.0, where it's all zeros, to this IP address, which is 200.23.17.55. And this tells, so if I advertise this site or prefix, then everybody knows that if there's an IP address in this range, that you would send it to me. Okay. Other questions about CIDR? This is fundamental in security and network security. You'll have to be able to figure out how to use CIDR notation. When we start specifying firewall rules and those sorts of operations, we're going to be specifying those rules using CIDR. Let's talk about a subnet walkthrough. Examples are the best way to get this into your head. Let's take a large block and split it into smaller subnetworks. I have this CIDR prefix 131.252.0.0/22. And let's say I want to split CIDR prefix into 4 equal subnetworks. But the way I'm going to do this is I'm going to expand out the prefix in binary. This is 131. This is 252. And then 0.0. And then I count up the number of bits, first 22 bits. And then this is the host part right here. Right. Now, the goal is to split this up into 4 equal subnetworks. Well, the first thing I want to do is figure out how many hosts are on this network to begin with. And so just like the previous example, how many bits can I use to specify all the different hosts on this network? And as it turns out, this is 10, right? This is 10 bits. And so the number of hosts in this CIDR prefix is 1024 to the 10th. So that is, when you see a prefix like this, you should be able to identify how many hosts this prefix represents. 1024. The next thing is, how am I, like, if I split this up into 4 equal subnetworks, how many hosts are going to be on each of those subnetworks? Well, you just divide 1024 by 4. And so you can split this up into 4 networks, each with 256 hosts on it. And then the number of bits that you require to denote 256 bits is basically 8. Okay, so when you want to subnet this thing into 4 parts, you're going to take the next 2 significant bits. And because 2 bits will encode 4 networks, you're going to say this now has to be part of each of the individual CIDR prefixes for each of the 4 subnets. So now I'm going to make this all red, where it's 00, and then 01, 10, and 11. And then the rest of the bits, the rest of the 8 bits, can now denote the hosts in each one of these subnets. That's the next part. And now I need to go the other way. It's like, what are the CIDR prefixes of each one of these 4? So the first one's easy because this is basically 131.252.0.0 again, but the number of bits that are in my network has increased by 2. So this is now 131.252.0.0 with 24 bits as the network part. Likewise, for O1, this is 252.1.0/24, 2.0/24, and 3.0/24. Okay. Does this CIDR example make sense for most people? Okay. Yeah. So, and you notice I teach this in the cloud class a little bit as well. It does take a lot of examples, but hopefully, like, this is so critical that I feel like it's worth repeating. Actually, was it? Yeah. There are 24 bits that are now the network part. Yeah. And so you'll see as this number decreases, network gets bigger, right? Like, so Portland State is 131.252. This is actually what we advertise. Like all 131, this entire campus, that's what we're going to advertise out the rest of the world. So it's going to be 131.252.0.0/16. Yeah, and then internal, and this is when I had that ISP B. Internal, we have all of these smaller routes, and then every router in the campus is routing on these smaller. That's all hidden. That structure is all hidden behind that full prefix that we advertise out to the rest of Yeah. And this is when we do investigations and we do like trying to do attribute. You are going to look at who owns the IP address, and that's given as a CIDR prefix. Like who owns this particular IP address is given as a CIDR prefix. That is down to who was allocated that by the Internet Registry, and this is how you can do attribution. Basically, get at the operator of a network that's not managing their network appropriately. Like, so for example, like there was an operator in the early 2000s that was notorious for allowing spam to be sent from their network. And eventually they're like, well, it came from this AS, it's in the Maldives. And then the political pressure was brought to bear on that operation to shut it down. And at one point, the level of spam increased by 75%. They shut that ISP down. And this is where the attribution, this is where the, I guess it's part of open source intelligence. That's where that information comes in, so you can actually do something about any attack that's being forced. We'll do a little bit of network intelligence later on. Okay, the other side of this, the aggregation part of this, is the reverse direction. And this is what we call supernetting. And so the idea is to take small blocks and combine them into one aggregated CIDR prefix to reduce the number of routes. Now, this has to be done very specially. Like it has to be aligned. It's sort of like a cache line. Like you have to take a full-on cache line to aggregate into one sort of tag. The same thing with IP addresses. They have to be aligned. The IP addresses that you're trying to aggregate have to be aligned on a good boundary, a power of two boundary. So here's an example: two Class C networks, 131.252.0.0 and then 1.0, and then is a /24. And so those host parts I represent as stars. And so if you look at these two prefixes, you can see if you wanted to aggregate these two together, they're well aligned because that next bit can be either a 0 or a 1. So you could specify as part of this that I want to combine these two things and then create a larger network where it's 131.252.0.0/23, where I've consumed this extra bit be part of the host, and I've taken away one bit from this prefix. And so this CIDR prefix can represent these two individual smaller networks. Okay, so this is a site I send people to, this interactive citer.xyz, that a really good visualizer for doing this kind of work. Okay, this is a long-winded way of getting to how CIDR and replication work in practice. So you have an ISP, ISPX. Say this is the local ISP, and then upstream is the regional one or the tier one even. And so let's say ISPX gets an allocation of 16 Class C network, 200.23.16.0, all the way up to 200.23.31.04. And so scattered about intentionally. Say ISPX has 4 customers, 4 companies that it's going to allocate these addresses to. And so there's a large company, a medium company, a small company, and a tiny company. And so it allocates 8 of these subnets. The large one, 4 to the medium, 2 to the small, and say one Class C network, the tiny, and it has an unallocated one left over. So that's basically the 16th one is unallocated. What you would do is ISPX is going to take these individual Class C subnets and will aggregate them in its routing table to be a single prefix. So for these 8/24s, it can combine all of those into a /21 with a 200.23.16.0 prefix. That's the first routing entry. And it says anything that matches this prefix can go on to interface 2. And this is how routing tables work, right? You've aggregated these 8 things. So I don't have 8 routes in my routing table. I have 1. Likewise, the medium company starts at 23.24.0, and there are 4 subnets here, Class C subnets, and so I can now aggregate those into a single /22, right? Because that is similar to that other operation we did for subnetting. There are 4 different networks can get aggregated into one. And then this goes across interface 3. Likewise, for 4 is basically 2 of these things, so it's a /23. And then 5, there's only 1 subnet here, so it gets its own route entry. And then for anything that doesn't match, you would implicitly just drop this packet, because this company hasn't allocated that space, so there should be nothing on there, right? Nothing should show up. Yeah. The way this route works is it's just pretending that there's one enormous network here that's a /21, where the host part could be any one of those 11 bits. At that, basically what this specifies. Okay, so the entire space. So ISPX has this allocation, has these individual routes. But it needs to advertise an aggregated route to ISPW. So ISPW can get the entire aggregated space, right? So you can combine all of this into a single /20. So this is 16.0/20. ISPW only has 1 route. And this is where you get routing scalability on the internet. And it's through CIDR and route aggregation. And this is done up and down the hierarchy, right? Okay. Suppose this last subnet that's unallocated is allocated to a new company. So we're going to say, I'm going to turn this from unallocated. Now I have a new company here using that prefix, and say it's initially connected to ISPX. And then instead, since this is interface 6 in this tool router, I'm going to change this route table entry to now go to interface 6. Okay. Now, if this company is like, ISPX the uptime on ISPX isn't as great, or maybe ISPX is really expensive, I actually want to multi-home my network to also get service from ISPY. And it's like, you know what, I prefer people reaching me through ISPY because the address that or the service I'm getting from ISPX is too expensive. It happens all the time. In fact, the state is multi-home, multiple providers as well. But I have this tiny CIDR allocation. And if you look, if I start advertising my routes through ISPY over to ISPW, I have a problem here. I might need to break up this gang, right? Because this thing included my subnet. All of a sudden, I want a different route to these addresses, but I still am matching this larger prefix. So what happens is that ISPW add a more specific route through Y, get to that prefix, and here you have an overlapping route, right? An overlapping range of addresses. So this is allowed because you want to keep aggregation as much as possible. You don't want to break this thing up, but you have to change the algorithm. You have to change the route lookup algorithm to handle multiple matches in your routing table. The way we do this on the internet is to resolve this with a longest prefix match is preferred, meaning that the more specific route match is the one you take preferentially, is the algorithm. Okay, so then that's basically what you would do here. The more specific your lookup is, the higher the matches with its net mask, more preference you're given to route there. Okay. It's critical when we talk about BGP route hijacking. Because adversaries are like, okay, routes aren't advertised or aren't authenticated, and I know the more specific lookup is going to win. So both of these things will come in handy for a hijacker. Okay, I'm going to get started. There are some special IP addresses that we need to be aware of when we are using the network. The first set of special addresses is what we call the loopback addresses. And this is specified as a CIDR prefix. So 127.0.0.0/8. How many addresses are part of the local host or loopback address if you have a /8? 2 to the 24. That's a whole bunch of IP addresses. Specify yourself. But that's what happens. 127, you're like me. An IP address that begins with 127. Yeah, that's localhost. That's a loopback. It's the self-talk addresses. So the internet talks to itself quite a bit. And that's a lot of addresses to talk about. I call this the machine's inner voice. This is, you can get access to the loopback interface on Linux. So if I do an ifconfig, these are all the network interfaces on my machine. There is a special interface called the loopback interface, and that typically has an address. Usually they use 127.0.0.1, but they use anything, and it specifies the same thing. It's yourself. Okay, so 127.0.0.1 is the most commonly used, but on Ubuntu and on with systemd and the way you can configure your DNS server on systemd, sometimes they'll use 127.0.0. the port number. And so for a local DNS server, the DNS port is 53. So sometimes they'll use 127.0.0.53 with a port number of 53 as the loopback in this case. This is important when you want to combine access to services on a particular machine. So services that you're running on your machine that you only want programs running on that machine to access, you would typically want those servers to listen on the loopback interface, because no external machine can connect up to your local interface. Only processes on the machine can connect up to that local back interface, and it will reject any other connection from external addresses. If you have servers on your machine that you want everybody to be able to access, then you want to accept connections on any interface, not just the loopback, but also regular internet, like the Ethernet interface, for example. And you specify that using the 0.0.0.0 saying anything, or a star sometimes in some of these. So here's an example on your local Linux machine. If you do a netstat command, say, give me all of the services that are listening on my machine. And so I'll do netstat-al, and you can see here that these particular services, they are listening on a local address that's the local host on that particular port. And so for this domain name resolution service running on this machine, and in this one, the Internet Printing Protocol service, are only possible. You can only connect up to those two ports if you're running a local program. So of course, you know, like if I have a print spooler on my machine, I don't want anybody to use my print spooler to print. I just want my local web browser, or maybe it's my terminal, my Xterm. I want to print my screen. I only want those programs to print. And so if I have this set up, then yeah, only those processes on that machine do the printing, and that's the thing. The other way is if I have services running that I want everybody to connect up to. So for example, on my desktop, everyone's connecting up to codelabs.cs.pdx.edu. I have to run a web server that accepts any connection, and that's where the star notation is. So for these two services, HTTP and for SSH, I am allowing anybody to connect up to those servers. Okay. I can also use a flag called -n to see the numeric addresses and the numeric port numbers instead of the name. So this is nice for a human readable format. If you actually want the addresses and the ports, you can see that, oh, the DNS one is using 127.00.53:53, and then this is the Internet Printing Protocol one, and then this is the two network connected servers. So this either a star or the 0.0.0.0 with that port number. Okay, are there questions about that? The next set of special IP addresses are the private IP address ranges. These are not routable on the internet. If you send a packet to a destination, one of these destinations, onto the public internet, it'll get dropped because there are no routes to these particular ones. Yeah. Yes. So TryHackMe is using the 10 subnet heavily because, yeah, it has to create a virtual network on the back end, and you won't be able to connect up to it directly. It's using those virtual addresses. This is why you have to log into the attack box. Right? And this is why, I mean, I realize, I see the traffic, I realize it's painful. And I guess if you don't have the VPN set up, both the attack box and the VPN are meant to get you onto like a gateway that is connected to the private network that gets set up for your TryHackMe account. That's what's going on underneath, and it's only for the ones that are multiple machine ones that require a private network that you have to do that kind of stuff. That's correct. We do that here actually, and so we're using the 10. The 10 subnet is the typical one I see people use. Although for home networks, 192.168 prefix is often by default used by these home routers. I barely see the 172.16 unless you're talking about Docker containers. And so you'll see if you're running Docker, if you've installed Docker on your Linux machine, you'll see that there's an interface there for the Docker interface. By default, these Docker containers you can communicate with over that subnet that it creates out of this private prefix range. So this is actually used to number all the machines in that particle lab over there. So like Catron, for example, if you do a lookup on Catron from external from Portland State, you'll get the Catron maps this 10 address. And so like you cannot connect up Catron from remote location using IPv4. Turns out Catron has an IPv6 address that you can connect up to publicly. It doesn't have a public IPv4 address. It's got this private one. So if I look it up and I try and SSH to it from external Portland State, I'll get no route to host. The network is unreachable, right? That packet gets dropped because that private address is only routable within the network that it's established in. Okay, so if you want to get to Catron, you first have to SSH into a machine that has a public IPv4 address and is connected to the private set of addresses, and that would be like Linux, like Ada. You SSH into that, it's got the public IP address, and then what you can do is from Linux, you can SSH into Catron, the 10 network. That all works. Yeah.
There's all of your like 190 bunch of kids.
Yep. Everybody's running a 192.168.something.something. But that's basically how you can do that. It's not publicly routable, but it's locally. Now,
So publicly routable, like you're still your local router has like.
so I don't know how much I'm going to talk about network address translation, but what's happening is those IP addresses are being rewritten in the network in order to be globally routable. Like you have a 192.168 address, but as you want to communicate over the internet, IP address that your router has. That's what's happening. So that hack is because we're running out of IP addresses. The goal of IPv6 was to give everybody a globally routable IP address, get away with this, get rid of this business, but we don't have that. And so the hack is to extend the lifetime of IPv4. We do this kind of operation. And I talk more about this in the cloud class, but not so much here yet. Okay. So the next thing I want to talk about is all of the, like where this stuff shows up. And you have seen this, I don't know if you noticed, but you have seen this with your Kali VM. When you bring up your Kali VM, there are a set of internal IP addresses that get allocated to it, as well as an external globally routable one. This is important because if you're doing a whole bunch of testing, security testing, if you're playing attacker defender, you want to do that in a private network and not in a public one. You don't want to bring up a vulnerable machine with an external IP address and then just have it get left, right, and center and then run up your cloud bill. And so you would have to, you can bring up these machines using a local internal address, and then maybe you allow connection to some kind of bastion server that can connect into it. And this is what's happening with TriHack. Bring up a whole bunch of machines that have like, bogus weak passwords. You don't want people to just own those machines like on the public internet, so they force you to use the attack box as a stepping stone. And then they have you do a VPN so they can get some attribution as to who's doing the activity. And that's effectively what you'll see. Well, This is why when you start bringing up some of the servers and the services later on in this segment, you'll be bringing it up and connecting to the internal IP addresses and not the external one. In fact, if you actually do some scanning on the external ones, you'll get a nasty gram from Google Cloud saying, why are you attacking other machines? So that's why following the directions of the lab is important. Otherwise, you'll get a warning from Cloud. And this happens every quarter because you're copying and pasting, and you're like, oh, there's 2 IP addresses here. They both work. Well, use the internal one. If it's Nmap or if it's any attacking thing, yeah, use the internal one. Okay, so this putting it all together on a Linux host, this allows you to then parse a routing table on Linux. All of these pieces that I've talked about allow you now to do a netstat-rn, which is like the routing table, and so this routing table, you see the different columns of it. It's like, well, what is the destination prefix of the route? And this is a combination of this prefix and this net mask. I know they're in like column, but think of those 2 columns as together. Then if you match this prefix, the next column is, well, where does it go? Where should I send this thing to? And that is part of this gateway and this interface, these 2 columns. So those are the 2 important things to talk about. And so the destination and the gen mask together say, what's the CIDR prefix? And so the gen mask is just basically setting all the bits that are part of the CIDR prefix. So when you see 255, 255, 255.0, this is the same thing as a /24. There are 8 bits here, 8 bits here, 8 bits here. So you'll see this in multiple formats. I'm just telling you, this is basically the way to specify /24. Likewise, this specifies a slash. This specifies that all the bits match. All the destination can be anything, and then all of these bits can be anything, or the range is this matches everything. Okay, but you can see already that this is a rule, a routing rule that matches any single packet, and then the more specific rules will go to different places. So the route says match. When all else fails, you're going to send the packet to the gateway, which is the default router. Okay. That's what these 2 columns are. So the gateway is what is the next hop, and then what interface do I use to get me there? Okay. The other part here is, so /0 matches everything. So by default, you're going to send it to this gateway. But you have these other routes. And you have a more specific route, which is right here. So this more specific route says that if you match this prefix, 131.252.220, first 24 bits of that, this says send it directly onto the Ethernet interface. Don't send it to the router. You can ARP directly for any IP address that matches this prefix because it's directly. That's my plan. That's the other route. And because this is more specific, I will, if I match here, I won't do this one. The other route that's here is this one. It says anything that is matching this prefix, 172.17, the first 16 bits of it. This is what Docker uses as its range of IP addresses. So you'll send that to the Docker 0 interface. And the Docker engine is sitting there listening to those packets and then routing those to any of the containers you're running on the back end. And if you don't know what a container is, that's also something that is covered in the cloud class, if you're interested. Okay, so all of that gets us finally to some attacks. And so we'll start with some attacks. The first thing I want to talk about is the IP security model. And then this is blank, because there wasn't one. This is all being bolted on after the fact. And so we talk about the CIA principles. Initially, IP had no support for confidentiality. You could have sniffers wireless network, sniffers on the internal network, and sniffers on your local area network. And all of these places would be able to expose information, your confidentiality. Moreover, we saw with the ARP spoofing, you can hijack connections by injecting yourself into the middle, and you can modify packets because you're in the middle. So this compromises both source integrity or authenticity as well as data integrity. So yeah. And then finally, availability. We have this issue where you can basically, as a server, bombarded by an innumerable number of bots that are controlled by an adversary. Initially, we had no way of saying, hey, stop. Hey, this particular set of nodes, can I have them stop traffic coming to me at the edge? Initially, we didn't have that to say signal malicious behavior on the edge. We're slowly bolting all of this stuff back in. And that's when we talk about network security, this is basically a remediation process that's going on in the network. Try and get these CIA principles into the network. At the edge, and then this is something I would have to explain content distribution networks a little bit and TLS a little bit more. I might be able, I think I'll add a little bit to the transport layer section. Basically, in fact, I'll talk about all of these cloud providers have DOS mitigation, where they are proxying connections at the edge and then just drop it there. So in this case, edge of these network location, you're able to drop it or it hits the public internet. Okay, let's talk first about the confidentiality attacks, so network sniffing. The protocols were initially in the clear. So FTP, Telnet, simple mail transport protocol, SMTP, which is still what we use to send email over the internet. The web protocol was in the clear. Mail access protocols were in the clear. Post office protocol, internet mail access protocol, IMAP was in the clear. This is a network management protocol. This is a lightweight directory access protocol. This is basically a directory service, like for username, password storage over the network. And then database protocols. And so because of all of this, all you needed to do was be really good at Wireshark, get all sorts of stuff. And that's what you can do now. Like if you get on the inside of a network, they're still using unencrypted protocols, you can get all sorts of credentials. And this is one of the things adversaries do when they get a compromised machine. Next step is a whole bunch of data collection. Try and move laterally to get credentials so that they can actually go somewhere else in that enterprise. So here's an example of Telnet. This is or SSH, where you just say, hey, Telnet to the server I want to access using the Telnet D sort of service. And then there's a protocol, and it's basically a wireline protocol that has the username and password go in the clear. You can think about SSH, but it's all done unencrypted. And so all you have to do is go into Wireshark, find the Telnet stream, reconstruct the stream, and then get the username and password. And of course, this this person actually had some typos. And no, wait, that's just echoing the output. Then you can actually get the username and password there, and then you're good to go. This is FTP, and there's a protocol for transferring files. And if your FTP server is protected by username and password credentials, all you have to do is be on the network. So if you're doing this over a wireless network that's unencrypted, you could just pull these passwords out. So there's an example of FTP. An example of SMTP. So if you're trying to authenticate access to your mail transfer server, you can see SMTP is used from the sender's ISP, from the sender's ISP to the recipient's ISP. And each one of these you could authenticate. When you do the authentication, you can see, oh, the username and password fields are sent in the clear. And this looks like it's encrypted, but this is just base 64 encoded. You can see it's anytime you see something like that with an equals, you're like, let me try and base 64 decode that thing, bunch of printable ASCII. followed by an equals. And of course, if you do a base 64 decode, we got the username and the password base 64 encoded. So again, that's an insecure protocol. IMAP and POP are doing something similar. So again, you base 64 decode these clear text payloads, so the request and the response, and then you can see the credentials going across. Here's a PostgreSQL reconstruction where you can see the parameters that are sent on this PostgreSQL connection are also sent in the clear. Here's an HTTP one. So if you are posting a form and it's done over unencrypted HTTP, you can click on the post. So say it's an API that allows HTTP posting rather than being HTTPS only, then you can pull out credentials accessing that API, like logging into it, and then pull out something that you can replay. And then here's one. This is particularly awful. This is an authentication protocol that's sending stuff in the clear. And so this is basically on the back end. You would authenticate to your LDAP server. You give it some credentials, and then you ask LDAP to say whether or not it's authentic or not. And then those credentials are sent in the clear. If an adversary gets on a machine, this is what we'll be looking for in the network traffic going back and forth. Try and pull out credentials. And if you haven't hardened your machine to only use encrypted communication, you might have an issue. Okay, the next thing is networking or integrity attacks. So IP spoofing is very similar to ARP spoofing. The idea is the adversary is going to try and hijack an IP address. It's going to impersonate an IP address at the network layer instead of the data link. Okay, so in the ARP spoofing one, you're trying to hijack it using ARP hardware addresses. With IP spoofing, you can actually fake identity of the source of that traffic, even if it's not part of the same network. When ARP spoofing, you're trying to imitate a victim that's on the same network. With IP spoofing, you can send it from anywhere. And the idea is to forge the IP address of any of the packets that you send as an attacker. Okay, this is allowable since the way we have implemented the internet protocol, if you want to send an IP packet into the network is trusting you to fill in source IP address. So there is no authenticity going on between the network and the nodes that are sending packets into the network. So in this case, anybody can be any IP address because it's just software and you're just entrusting people to implicitly not forge the entry, the source IP address. And well, of course, this is something that's not, it's a bad assumption. And this ends up leading to connection hijacking, connection spoofing, able to establish blind connections with a remote host where you're going to fake a connection between a victim and a remote host when you're not even in their network. And that's what blind connection spoofing is doing. Or you can blindly reset a connection. So if you have two routers and you want to mess up routing, you can forge a reset from one router to the other, disrupt the connection, force them to re-authenticate, and then you can continually reset that connection to disrupt the operation of the network. And this is all done because we don't authenticate the source of the IP address. At least initially we didn't. Now we kind of do, we do some things to protect against that. Well, the first example I want to talk about is you have an adversary. This is all on the same local area network. You have an adversary, this little Pac-Man person, and then this Pac-Man person is at 0.111, and this is Bob over here at 0.113, and you see the hardware address is 01, and this hardware address is 3. The first thing you can do as this malicious user is to forge the source address so that this malicious user, malicious Pac-Man, can frame Bob for a packet he can send. How would you do that? Well, you would just construct this Russian doll, some attack code, and you send it to some web server, say you want to frame Bob, having him look like he's bombing like Portland State, like the Portland State website. And then you say, okay, well, this is going to the Portland State website, perhaps. And then say this came from Bob. So that's 1.13 is Bob's IP address. And then this will get, you can actually forge Bob's MAC address. So if you've been listening to this and if you've ARPed for Bob's MAC address and you've gotten, well, you can, this is actually, if this is 03, it would be a proper frame. I think that should have been an 03. So I can properly frame Bob by forging all of this stuff to make it look like him. So it's probably not a good thing to have in your network. Yeah, anyone who checks this will think that Bob, assuming that 04 was an 03. I don't know how that got in there. I can also frame someone that's outside of this network, right? So here's another attack packet. I am like, oh, you know what? I'll just send this to Portland State's web server saying that this is from some random IP address that's not from here. And in which case, this gets routed through the internet and the destination thinks it came from here. It has no idea where the actual source of that packet was, right? Like 10.1.2.10 could be somewhere like halfway across the planet. And it got sent here with someone forging IP. Yep. Kind of. No. Well, so stealth scans are something different, but this is a stealthier thing to do for an adversary. Yeah. We'll get a little bit. We won't do too much with the stealth stuff because I have to do other things in this class. But yeah, well, now you're starting to see how sneaky things are. That's the important thing. That's the big home point for the module, is how sneaky you can be. Okay. So this all of this stuff gets us to finally route hijacking, which is an integrity on the routing infrastructure of the routing aggregation stuff. We have seen routes that are preferentially taken. We know that we can spoof advertisements. And so the attack is to spoof a more specific route to a victim in order to redirect that victim's site towards an autonomous system that the adversary owns, or the adversary is in. This is the network layer equivalent to that ARP poisoning attack, because you're doing this across multiple hops in the internet. And so that's the strategy. The adversary sends bogus routing information, says that it owns route to a particular victim, and to send all the victim's traffic to the adversary rather than the original victim. We'll slurp up all of that traffic, figure out what's in it, modify it potentially, and then send it to the original victim. Or not, in this case. In many cases, or not, but like you could actually send it back along to the victim. So this is used to impersonate an arbitrary site on the internet. So now you can get all of the victim traffic, you can inspect it and resend as you like, and you can capture all of the stuff that's unencrypted that's going across that network. So here's just one example of a route hijack. I have a local DNS server, and it's trying to communicate legitimately to a root DNS server, and we'll talk about DNS later. So there's the original connection. If the spoofed root server, if the adversary is over here, injecting bogus routes, more specific bogus routes to this root server, then the idea is that that traffic could then get redirected to the spoofed server. Okay, so people attack this all the time. There have been successful attempts. It lasted several hours at one of these major ISPs that host some of these root servers. And the problem here is that any response, because DNS is also not authenticated, any response is believed. So that's an issue. Okay, so BGP route hijacking has been featured in many incidents, some recently. So Pakistan did this to YouTube because they were trying to like rid of YouTube locally. They're like, yeah, YouTube is really subversive, so we're going to take those IP addresses that belong to YouTube, and we're going to advertise that their route was to dev null. They're going to black hole that traffic. In doing so, because they're just targeting the YouTube address, Google is aggregating and advertising a larger prefix around. So when Pakistan decided to say, you know, hours is this? 14 hours? For a while. This happened. No, it doesn't say. I think it was like 14 hours. They undid it. Google did this accidentally to Japan. So I like this because they're like some engineer ordered the BGP advertisement and then overextended the CIDR prefix to include all of Japanese all the IP addresses that had been allocated to Japan. There's a wiped Japan off of the internet. So that was an accident. This could be intentional or by accident, and both have happened. This seems intentional. This is what Russia did, Google, Facebook, and Microsoft addresses. That can't be an accident when you target like the top 3 places for traffic. And then this probably wasn't accidental either. This is what Ukraine did to Russia recently over the summer, try and get traffic hijacked. This is now, so all of this stuff is like nation state kind of stuff. Now just garden variety criminals are doing this. So here's example number 1 from earlier this year. Criminals wanted to check network traffic going to content distribution networks that sourced critical JavaScript files. If you're doing web dev and you're like, oh, you know, this JavaScript framework file that I'm pointing the script source, wherever that framework URL is to pull that script. If that script is managing your cryptocurrency wallet in JavaScript, and if you poisoned that script content, basically capture the private key of a wallet and send it somewhere else, you can get everyone's private key and you can make money. That's what this thing is. Okay. Play swap crypto users. What they did is they hijacked GP, and while the network was being hijacked, they could issue themselves a certificate that made the traffic look. So the signed certificate, the TLS certificate, click someone says, I have the address, I can someone have both. I can actually get that TLS certificate, and then that's what so full end-to-end hijacking, whereas DNS, TLS, and BGP being coordinated. To how much was this worth? $1.9 million is basically what happened here. And there's a picture of it. They shifted all the traffic. I think blue is the blue is the normal server, and then they shifted so they hijacked the route. So again, this is the CIDR prefix of the larger allocation. They hijacked that route with a more specific advertisement, and then they redirected all of that to the attacker server, and then they were able to issue certs, redirect client traffic, and then capture this money. That was earlier this year. Here's another one that came across 2 months ago. This is a cross-chain bridge that's used to do cryptocurrency, the smart contract. And basically, someone did the exact same thing, a BGP hijack, in order to get access to sellers' network traffic on AWS. They're advertising a more specific route to AWS infrastructure that they know is being used to run the cross-chain exchange. And the seller network saw that this was happening and immediately tried to get AWS to do something about it. And it took 3 hours. And as a result of just 3 hours, they lost almost $250,000. But this is actually pretty good in terms of a response. Like 3 hours is pretty good, but you could still. This is why I like when I teach cryptocurrency class, it's like, don't buy any. This is why you wouldn't buy any. You're like, oh, they're going to hijack your JavaScript file and get your private key, or oh, they're going to hijack this exchange and then wipe the exchange out of all of its assets. and then you'll have nothing. Like, that's my public service announcement to people. This is the post-mortem on that, and you can see that this more specific route got advertised as a /24 and then withdrawn as part of it. And then as the adversary controlled this prefix, the adversary was able to get a TLS cert issued to it. And then basically this go get SSL service issued that TLS, a valid TLS cert for that adversary server. And then they were able to get the client to believe that they were actually the real thing. Assuming that they copied the website verbatim also as part of it. Well, a very intricate exploit required a lot of moving pieces, but now at least you can understand how this thing happened. Okay, some defenses, filtering based on prior information. So this at least notifies people when it happens, like when a hijack happened. But this also messes with the fault tolerance of the network. You want the network to be able to react to changes and make swaps. Like, how do you tell between something that's legitimate, a legitimate swap versus someone that's hijacking something? They have tried to bolt on a public key infrastructure for exchanging routing messages, GP messages. It's been really fraught with deployment issues. We don't have widespread adoption of that. What we do have is our tools continuously monitoring and detecting abnormal changes. And so in your NOC, your Network Operations Center, you might be looking at this. And some of these tools like route views, this is actually something that University of Oregon folks participate in a lot. Monitoring BGP, monitoring all the routes, and being able to visualize what the routes are doing underneath is something that most providers are doing now.